All right, so today we're talking about splitting reality. Seriously, we're diving into nuclear fission, which is, without a doubt, humanity's most powerful and complex reaction. We're talking about harnessing the fundamental forces of the entire universe. And it's all for a goal that is, well, surprisingly simple. Let's get into it. So let's kick things off with a little thought experiment. Imagine you've got 1 kilogram of uranium right here and 1 kilogram of plain old sugar right here. Now, thanks to Einstein's famous equation, E equals mc squared, if you could magically convert all of their mass into pure energy, you'd get the exact same amount from both. The thing is, turning sugar into pure energy is, well, it's basically impossible for us. But uranium? Oh, uranium is a completely different story. It's practically begging to fall apart.
And the amount of energy we're talking about here is just, it's absolutely mind-bending. That 1 kilogram of uranium, it holds enough energy to fully charge 300,000 Teslas. 300,000! Now, to put that into perspective, you'd need to burn 10,000 kilograms of coal just to charge 1 Tesla. The difference in energy density isn't just big, it's staggering.
So, okay, this raises a pretty huge question, right? We've managed to figure out this incredible cosmic-level physics. We've unlocked a power source that's basically a star in a box. So, for what? What's the grand ultimate purpose for harnessing all this power in a power plant? You ready for this? It's used to boil water. Yep, that's it. All that brain-breaking science, all that cosmic power, is used to get something really, really hot. That heat boils water, which makes steam, and that steam spins a turbine. We've literally created the world's most powerful, most complex, most expensive tea kettle. So how in the world does this cosmic kettle actually work? I mean, how do you get from a chunk of metal to boiling water? To get that, we need to zoom way in. I'm talking down to the atomic level, where we meet the force that holds pretty much everything together. Think of it as the universe's tiniest, but also its strongest superglue. Okay, so let's think back to basic physics for a second. You've got the nucleus of an atom, and it's jam-packed with protons. Now, all those protons have a positive charge, and if you remember anything from playing with magnets as a kid, you know that like charges want to fly away from each other. They repel violently. So why doesn't the nucleus just instantly fly apart? What's holding it together? Well, the answer is something called the strong force. It's one of the 4 fundamental forces of nature, and when you get down to these tiny, tiny distances, it is by far the most powerful force in the universe. It's that cosmic superglue we were talking about. It grabs onto the protons and neutrons and holds them together so tightly that it just completely overpowers their natural urge to repel each other. But, and this is a huge but, this superglue has a critical weakness, a fatal flaw, you could say. And that is its range. The strong force is incredibly powerful, but only over an absurdly short distance, about 1 femtometer. That's a quadrillionth of a meter. It's just an impossibly small distance. You go any further than that, and its power just vanishes. Poof, gone. And this is where the problem starts for big, heavy atoms like uranium. See, the nucleus of a uranium atom is about 11 femtometers wide, but that superglue? Its range is only 1 femtometer. It's like trying to hold a giant redwood tree together with a single, tiny staple right in the middle. The center might be solid, but the edges are just not. So what that means is that the outer edges of the uranium nucleus are just too far away to feel the grip of that strong force. And out on those edges, the other force, the electromagnetic force pushing all the positive protons apart, it starts to win. And that is exactly why uranium is radioactive. It's just too big and bloated for its own good. It's fundamentally unstable, so it's constantly throwing off little particles, trying to get down to a more manageable size. Okay, so this natural instability is the key to everything. But there's a big difference between a slow, natural decay and the massive, instantaneous explosion of energy we need. So how do you make that happen? Well, you have to kick off a chain reaction, a domino effect that unfolds in a literal trillionth of a second. What scientists figured out is that the perfect trigger is just 1 single neutron. If you fire 1 neutron at just the right speed into that big wobbly uranium nucleus, it's like giving a gentle nudge to a giant boulder that's perfectly balanced on the edge of a cliff. That tiny little push is enough to destabilize the entire thing and send it crashing down. And here's where it gets wild. When that 1 neutron splits the first atom, 2 things happen. First, a ton of energy is released. But second, and this is the crucial part, it also spits out 3 new neutrons. Now, those 3 neutrons fly off and hit 3 more atoms, which then split and release 9 neutrons. Then it's 27, then 81. It's an exponential chain reaction that just explodes in a fraction of a second.
But wait, where is all this energy actually coming from? Well, it all goes back to E equals mc squared. See, if you were to take the pieces left over after the split, in this case smaller atoms like krypton and barium, and you put them on a scale, you'd find they weigh just a tiny, tiny bit less than the original uranium atom. That little bit of missing mass wasn't destroyed. It was converted directly into a massive amount of pure energy. Now, this incredible chain reaction can basically go down 2 very different paths. If you just let it run wild, completely uncontrolled, well, that's a nuclear bomb. But if you can find a way to manage it, to control it, that's a nuclear power plant. And that's what they do. They use these things called control rods, which are basically like sponges for neutrons, to soak up just enough of them to keep the reaction going at a nice, steady, manageable pace. Of course, harnessing this kind of power, well, it's not free. There's a price to be paid. It leaves behind a receipt. And this isn't the kind of receipt you can just toss in the trash. This one sticks around for a very, very long time. We're talking about the byproducts of fission, better known as nuclear waste. And this stuff, it stays dangerously radioactive on a timescale that our brains just aren't built to understand. We're not talking hundreds of years or thousands. We're talking, in some cases, for over 1 billion years. So what's the brilliant long-term solution for this billion-year problem, you might ask? Well, the official international consensus is, and I quote, that the best path to take is to bury it in a really deep hole somewhere. That's it. It is the ultimate corporate, not my problem strategy. We're basically just kicking the can so far down the road that it won't be a problem for anyone listening to this or their great-great-great-great-grandkids. Now, a question that always comes up is, hey, why don't we just shoot it all into the sun? And, it sounds like a good idea until you think about the risk. Imagine a rocket packed full of the most toxic stuff humanity has ever created, exploding on the launch pad or in the upper atmosphere. The fallout would be a planetary-level catastrophe. It's a risk so unimaginably high that nobody is ever going to sign off on it. And that brings us all the way back to where we started. We figured out how to crack open the very building blocks of reality, an incredible scientific achievement, all for the mundane purpose of boiling water. But the process creates a toxic receipt that will outlast our languages, our countries, maybe even our entire species. And so the big question we have to ask ourselves is it worth it?